Okay, well, such a subspace is interesting if a set of points cluster within the subspace. Well, we talked about that before, but that means, on the other hand, that the points may exhibit high variance in the perpendicular subspace. So this is the perpendicular subspace. So S here, S plus A, is the interesting subspace. This is the plane here, yeah, the hyperplane, and perpendicular to this hyperplane, the points may spread all over. Yeah, so because this here is this is just one direction because it's a three-dimensional example, but that may be, of course, also multidimensional because those are the directions that are not interesting for the subspace. Yeah, so we may have an arbitrary hyperplane of arbitrary dimensionality, which is relevant, and if we project all the points onto this hyperplane, they cluster, yeah? And along the perpendicular subspace, the points may exhibit any variance, typically a high variance. Yeah? So the perpendicular subspace is denoted as perpendicular plus A here, and here in the figure, please don't get confused. This is the old term that is not perfectly correct. Formally correct, so this should be S perpendicular plus A, and yeah, that's the same figure as before. So here in the perpendicular subspace, S perpendicular plus A, they may have an arbitrary variance, and we don't care actually. Yeah? So in general, points on a hyperplane appear to follow linear dependencies among the attributes that actually span those hyperplanes. Yeah, so we had now a different view here, exactly the different view to this one here. So now the points are, so here are the points on a line, actually the line that is perpendicular to the relevant subspace, and the same holds true if we have the other way around. So this point, those points here are on a common hyperplane, so they have a common correlation among some attributes, and the perpendicular subspace here now is the relevant one. So in this case now is the relevant one, because if we project all those points on this line here, in this case on this S plus A, this is the line now, they are all extremely similar, so they cluster. Yeah. So once again, in general, the points on a hyperplane appear to follow linear dependencies among the attributes that span the hyperplane. Yeah. And the perpendicular subspace is the interesting one. Yeah. So how can we capture that? Well, that somehow, if we take a step back here, here. So we have some high variance directions and some low variance directions that span. The low variance directions obviously span the relevant subspace, and the high variance directions obviously span the non-interesting subspace, which is perpendicular to the relevant subspace. Yeah? So that somehow sounds like PCA, right? And actually PCA can be extremely valuable to capture that. Yeah. So assume we know the cluster members. How can we capture the relevant subspace? Well, we could apply PCA to the cluster members. Yeah. So in order to find the directions of high or low variance of a set of points, we could just apply PCA. Yeah. That is, of course, given that we know the cluster members. If we don't know the cluster members, we will talk about that right in a minute. Yeah. So PCA revisited, we could compute the covariance matrix of those cluster members. Yeah. And then then do the eigendecomposition. Well, we talked about that before, which gives us D eigenvalues and the D-dimensional eigenvectors. And the eigenvectors actually are the directions that are important. And now we need the additional information of the eigenvalues, because the eigenvalues tell us what are the directions, what are the eigenvectors with the high variance, and what are the eigenvectors with the low variance. Yeah, because we need the eigenvectors with the high variance, which are those two here in that case. Those are the subspace which is perpendicular to the interesting one. So we need the subspace with the low variance in that case. Yeah, other than we did that before in feature reduction, because those are the subspaces, or those are the directions of low variance, and we want to have the subspace with low variance now because we want to cluster. Yeah? So we have to look at the eigenvalues for the eigenvectors and retrieve the ones with the small values, small eigenvalues. Those are the eigenvectors, the directions spanning the interesting subspace. Okay, and that is captured here. So if points of the cluster form a lambda dimensional hyperplane, this hyperplane is spanned by the first lambda eigenvectors. Yeah, so those are the directions of high variance. So here, for example, the non-interesting subspace in our intuition. Yeah, we call them the strong eigenvalues. Yeah, which is a little bit unintuitive, but anyway. So, and they are denoted by this snake V here, and the others are called the weak eigenvalues, which are d minus L eigenvectors, which have the small eigenvalues. Yeah, and they are denoted by V hat of d, and those actually span the interesting subspace, and those actually span the hyperplane on which the points are located. So this is the basic, or the important distinction here. So the strong eigenvalues, in this case, in this example here, the strong eigenvalues would be those two that span the hyperplane on which the points are located. This hyperplane actually is the correlation. Yeah, so this reveals the correlation. And the weak eigenvalues are, in that case, is only this one here, the small one here. This is those eigenvalues, eigenvectors span the interesting subspace. So the subspace in which, if we project all those points into this subspace or onto this subspace, they are all similar to each other. Yeah. So this is the difference between strong and weak eigenvectors. So from a clustering point of view, we are interested in the weak eigenvectors. From an explainable point of view, we are interested in the strong eigenvectors because, as I told you before, the strong eigenvalues somehow describe the correlations or the correlation those points here have in common. Yeah. Yeah, so for the eigensystem, the sum of the smallest d minus lambda eigenvalues is minimal under all possible transformations. We know that from before, so we know that the d minus lambda eigenvalues are really those guys that have the smallest variance among all the points. So if we somehow have a good idea on how to choose this lambda, we are sure that the points cluster optimally dense or have the smallest variance in this d minus 1 and minus lambda dimensional subspace, which is in that case a one-dimensional subspace here in this example. Yeah, so lambda would be two-dimensional here, 2, yeah, because we have a two-dimensional hyperplane on which the points are located on, and since we have a three-dimensional feature space here, original feature space, we have one eigenvector left. So 3 minus 2 is one eigenvalue or eigenvector, which is or which spans the interesting subspace, and there the points are mostly or optimally dense or optimally small, have an optimally small variance. Yeah? Okay, so the subspace where the points are points cluster is spanned by the weak eigenvector. That's what I told you before. Okay, so a general cluster model now can be derived from those observations here. So a general cluster model for correlation clusters, we just have to consider lambda dimensional hyperplanes that accommodate the points of a cluster. Yeah? And those are defined by an equation system of d minus lambda equations for d features, d variables, and some affinity. For example, we could use the affinity which we used here as the A, which is actually the affinity, affinity from the origin. Yeah, and we can use as affinity here. We can use, for example, the mean vector of all the points of the clusters. Yeah, and then the eigensystem, the equation system looks like this one here. So we take all the weak eigenvalues from here, yeah, the weak eigenvectors from here, and take the x's are actually the points, the cluster members, and this is the affinity. And all the points that lie on the same hyperplane, so if the points lie perfectly on the same hyperplane, all those points fulfill this equation. Yeah? So the equation system is perfectly fulfilled for all points if the points are perfectly on the same hyperplane, like here. But well, in reality, if we look at this one here, in reality, the points will probably not be perfectly on the common hyperplane. So in this case, it's a line. Yeah? So in that case, we have to allow for some jitter. So in that case, we say that the equation system is at least approximately fulfilled for all points of the clusters. Yeah? And this is a quantitative model for the clustering, for the cluster actually, and we can even use it for probabilistic prediction, for example, for classification. Yeah. But the more important part is that this equation system explains the correlation of the points in the cluster. Yeah. So yeah, just one note: correlations are observable. Linear dependencies are merely an assumption to explain those observations. Yeah. So this is again somehow the question. Well, we see some patterns like correlations here, and we try to explain them by linear dependencies. Yeah, that's it. Yeah. So the predictive model allows for the evaluation of this assumption and some experimental refinements. So the assumption would be there are some correlations. We apply this model here, and then we can as a predictive model, and then we can try to evaluate this predictive model in order to check our assumption, whether or not the assumption of the correlation was true or not, and probably refine experiments later on. Yeah?